So, hello everyone, welcome to our first SOUG Virtual Day. Before I give the word to Jasmin, I would ask you to write your question in the chat. And at the end of this presentation, I will ask the question to Jasmin and she can give you an answer. So the first presentation is about predicting skier days. Jasmin Fluri will present this, and so I will give to her the word. Jasmin, it's all yours.
Thank you, Flavio. So also a welcome from me to the first presentation of this morning of this Swiss Oracle User Group Virtual Conference Day. I have the pleasure of starting this day with the topic of data mining. My presentation today focuses on learnings of a data mining project and the prediction project I have done last year. It will show you how you can start when you want to do predictions yourselves with Oracle data mining, and it shows what the database is offering you. We will also have a look at some basic math, but you don't need to be scared here. Everything will be fine. If you have questions, please ask them in the Q&A. I'll try to answer them at the end of the presentation. We'll probably have enough time. Now, first, something about me. My name is Jasmin. I'm a database developer, and since last October, I'm part of the Oracle ACE program as an ACE associate. I work mostly in data engineering and focus on efficient development processes. My topics that I work with are mostly testing and continuous integration. I also do PL SQL, and I work a lot with data warehouses and data marts. So why do I talk here about data mining today? You cannot find data mining as one of my main activities because it's not. I'm currently finishing my master's degree in business information system and computer science. And part of this is research that we do together with companies. I'll explain later a bit more about this. You can also find me on Twitter if you like. And I also have a blog on Medium where I write blog posts. Now, what are we going to see during this presentation today? What will I talk about? We will start with an overview of the tasks that we had at hand. What was the goal and what should have been achieved in our project. Then I continue with how we proceeded and what the prerequisites were of the project itself. Finally, we will have a look at how we did the implementation, and I think we have really enough time for questions at the end. Now, why is this presentation about data mining? As I said before, I'm currently doing my master's degree part-time in business information system and computer science. And one part of the master's degree is doing research in university projects. And those research projects are usually conducted together with industry partners. Now, last year's topic was data mining and predictions. So we got a prediction research task that we needed to solve. The industry partner then presents his task to the students and involves them. Our group of 3 was lucky to get a Swiss skiing area as an industry partner. For me, as a skiing fanatic, this was all I could wish for, the perfect domain for me to find solutions in. Now, what task did our industry partner need to solve? A large skiing area in Switzerland consists of many, many different components. They have ski lifts, they have restaurants, they have staff for operating the lifts, staff for restaurant, of course, staff in search and rescue, as well as administration and back office. Usually, they are organized like a normal enterprise. The difference they have to a normal enterprise is that they have a large variation of their staffing, depending on how many people go skiing at a certain day. And this depends, of course, on the day of the season, but also on the weather, on the snow, and many other parameters that influence this decision if I want to go skiing or not. This means some of the staffing must be operating on all these days of the season, but others, like the restaurants, need less staff when there are less skiers in the skiing area. So the staffing varies with the amount of tourists that visiting the area. So the task at hand was to predict how many skiers are going to be in the skiing area on any given day in the season. The reason they want to know this is that they want to be able to plan the amount of staff they need on the mountain ahead. If there are not many skiers in the area, they also don't need to be many waiters in the restaurant. If it's a sunny weekend, they expect to have more skiers, and the restaurant needs to have all the staff available. So the amount of staff on the mountain correlates strongly with the amount of skiers expected to ski on the mountain. Having a proper amount of staff on the mountain also means saving costs. If they have too much staff on the mountain and only few skiers, that means that they have higher expenses. Since skiing areas are usually profit-oriented enterprises, they also want to keep their costs very low to improve their revenue. Now, if you want to start a prediction, you need data, a lot of data. Let's have a look where we got that data from. A first set of data was provided by the skiing area itself. They provided historic skier data for the last 10 years, so we knew how many skiers were skiing in the last years on a certain day in the past. They also gave us information about their visitors, the countries of origin, the duration of their stay, and some other informations. From fcal.ch, we took information about holidays of the different visitor countries. On the portal of Meteo Swiss, we got data about the weather of the past 10 years, like the wind speed, snow, rain, barometric pressure, humidity, and all the weather information that you can possibly think of. There's really a lot of data on that platform. On the Swiss Open Data portal, we got historical data about the national economy over the last 10 years. When we gathered all that data, we realized it was a lot. Not in volume, we only had a couple of 100 megabytes, but in variety, because only the weather data consisted of more than 100 features in the data set. We will discuss the challenges of that later with having a lot of different features when it comes to the creation of the data set. Now, what tools did we use to make our analysis, or what did we decide to use? As a university project, we had the given requirement that only 3 tools can be used for the research. So we decided to use Oracle Autonomous Cloud as our data store and machine learning platform. We only used the tools of the Always Free database and not Oracle Analytics Cloud because that's not a free tool. The second tool that we used, because we needed to decide how we are doing our data analysis. We needed to know if our data is skewed, how it is distributed, and for this we used Tableau. We're not very proud of this, so let's just forget about it and not go into much detail. For the data engineering part, we used SQL Developer. We discovered later that with SQL Developer data mining extension, the same thing would have been possible to achieve as with Tableau, more or less, for what we are used it. It was a bit late though. The SQL Developer data mining extension lets you analyze how your data is distributed and gives you an idea of how much variation in the distribution you have. So we could have just used the data miner extension and use only the 2 tools. Now we have decided upon the tools that we are using, but what else is necessary if you want to start a prediction? What do we need if we want to predict how many skiers are going to ski? Mainly you need three things for a successful prediction. First, you need to have a bunch of data, as I said before. And this should be historic data of the factors that influence your prediction. In our case, it would be useless to have flight information because people rarely go skiing by plane. But it would be useful to have the dates of the local holidays, for example, because people tend to go skiing more often on weekends and public holidays because they have time then. The second thing is to know what you want to predict. Just having a bunch of data doesn't automatically provide you with wisdom. That's why it's important to have a well-formed questions you want to answer with your data. It's a lot easier to work on a well-defined target and also know when this target is reached. It is also good to know when you have to stop optimizing your model. For this, you need to have certain criteria that you have to be met, like the prediction must be 82% accurate. The third thing is you should have some basic statistical knowledge. Not a lot, really not a lot, but some basic understanding of statistics will be necessary to interpret your data mostly and make statements about the accuracy and precision of your predictions. The rest you can compensate more or less with very good Googling skills, or how it was in my case. I luckily knew people that could help me figuring things out and told me how to go forward with it. So when it was crucial, we luckily had help here. Now, if we want to predict something, where do we start? We start with asking the questions that we really want to have an answer to. Because if you don't have a question, it would be a waste of time to do all the engineering work when there's no real outcome of it. And because, based on the question, it might also be that you have to get different data. Because different questions have different factors that influence their outcome. Now, if I ask, at which wind speed do we have to stop the lifts because it is too dangerous for the people? I probably need weather data and engineering data of the lifts to make this prediction, but maybe also some sensor data of how the lifts react in real life to the wind. If I ask our question that we had, how many skiers are in the skiing area on any day in the next 10 days? I don't need any engineering data because that's not really an influence here, but probably some data from the past years along with weather data and economic data. The third example question, how many skiers eat spaghetti in the skiing area on any given day in the season, can then probably be answered with restaurant sales data and the data of sold tickets. But maybe there are other factors that influence spaghetti consumption on a mountain, and we are not aware of them. And that's why prediction is always also an experiment you have to do. You can experiment with the data that you have, but you can never be sure if you have missed vital data. That's why you should analyze the data that you have very well. Maybe there are factors that are completely irrelevant that you see as vital for the prediction, but that would falsify your results. Now, if I have a question that needs to be solved, how do I need to prepare the data that I've gathered so that I can use it for my model, for the training of my model? The goal must be to have one single table that contains all the necessary data to train or test the model that you have. So we need one table where each row is one data point. The granularity must be consistent. So either you have data points per hour, per day, per unit, per year. It must always be the same unit the data points are measured. We decided to have our granularity in days, since our prediction question was how many skiers per day will be on the mountain. So the granularity was an easy decision for us. The data also needs to be very well labeled, that you know exactly what is in which column. It needs to be annotated and cleansed. This means you have to resolve keys that are not self-explaining, and you have to aggregate numbers to the granularity needed. If you don't have them in the granularity that you want to have in your data set, for example, if you have snowfall data per hour, but want it per day, you need an aggregation for this. Now, if I have all the raw data, the logical next step would be to arrange my data set, as we said. Now, let's have a look how the data set needs to be arranged exactly. When building a data set, you should aim for a diversity of data. You should gather both internal and external data. So when you're a company or a skiing region, for example, the goal is to build your unique data set that will be hard for your competitors that do the same thing to copy. That's why we took the internal historic data that we had of the skiers, as well as some external data like the weather data and the economic data that was external and publicly available. Data mining applications do require a large number of data points. But this doesn't mean that your data set needs a large number of features. The important thing is we want meaningful data related to the project. You may possess rich, detailed data on a topic that simply isn't very useful. That's why you should reduce your data to the one that you really need. You should also make some assumptions about the data that you require, and be careful to record those assumptions so that you can test against them and to assure that they fulfill your standards. We said before that reducing your data is very important. This process is called feature selection. Every row you want to have in your data set table is called a feature. A random brainstorming, like we did it at the beginning, of possible features often results in a large list of features. Not all of them are necessarily helpful to build effective classifiers. So selecting only a subset of your initial attributes can be a good idea because it decreases the complexity and the computing time of the algorithms that you use. And some algorithms are not good at dealing with irrelevant or redundant attributes and will deliver a lower quality if attribute selection is not performed. So the more noise is in your data, the worse the algorithms will perform. For example, it is important that the attributes don't correlate well with each other. They should be independent. An example of two features that correlated a lot in our data set was the wind speed and the air pressure. The wind speed is determined by the rate of air pressure change between two air pressure areas. So the greater the pressure difference, the faster the winds are. So those attributes would provide us more or less the same information. And we had to choose only one of them to not falsify our results. If we have decided which features are useful and which ones we want to use in our data set, we end up with a set of our final features. Only a small amount of them and not all of them. Now we have decided of the features that we consider useful in our data set. What are we going to do if values are missing in our data set? Missing values are a very common problem. Either there is no data point or it is not complete. Both cases are a problem for many algorithms because they cannot deal with them or are misinterpreting them. So while building the data set, one has to find a solution on what to do with those missing values. There are 5 possibilities that you see here, how you can treat missing values. The first one is data objects with missing values can be eliminated. This would result in deleting the row in the table. The attributes with missing values can be eliminated also completely from the data object. This would result in deleting the column and therefore deleting the whole data feature. For missing data, it's also possible to insert a special value like not available and later ignore those values in the analysis. It's also possible to insert a summary value like the mean or the median for missing values, or for categorical values inserting the mode. The 5th possibility is to copy the value from the data object that is most similar in terms of all other attributes and insert this value into the missing value. This is the most often used way of handling missing values. There is also a general consideration on building the data set that you should keep in mind. Larger amounts of training data often outperform more sophisticated modeling methods. That means that if you have a very large amount of training data, you could just choose a more efficient algorithm that has a lower accuracy, but a greater speed if you have a really large training data set. So instead of only using a sample of the data, that needs a highly accurate algorithm to cope with. So if you only have a small amount of data, the accuracy won't be very good, as seen in the picture here. If you have a lot of data, it improves the quality with every data set that you have. So if you can, always train your model with a very large data set. This is also the reason why you should keep your data inside the database while training your model. You have the performance and the security of the database and are unlikely to run into performance issues. If you export your data into some CSV file and then train your model on your local computer, you're probably unable to use the same amount of data for training, and you most certainly don't have the same performance that you would have inside the database. Let's go shortly back to some basics. Let's have a look on data mining and what data mining is, so that we know what we are doing here. Data sources can have very different shapes. They can be other databases, there can be flat files, there can be newsfeed, IoT data that are read. And this data is collected and pre-processed and is then stored inside a data warehouse, for example. Based on the collection of the data in the data warehouse, data sets can be put together. Important here is usually the data to the algorithm. It just makes your life a lot easier. So you create on the data of the data warehouse. Once you have your data set, so creating a data mining model or build data clusters, whatever your use case is. Those predictions are additional information that to your knowledge that you already have. This can help you take the right actions when those predictions or categorizations are correctly interpreted. So we end up with this data mining process. So the goal of data mining is to extract information from a data set and transform this information so that it can be used further. Data mining is divided in supervised and unsupervised learning. With supervised learning, the algorithm learns on a labeled data set and tries to find a specific solution to a questions that you have and it's done with classification or regression. So like in our example, we had a labeled data set where we knew exactly what data is provided to our model. With unsupervised learning, the algorithm learns on an unlabeled data set and tries to find his own pattern in the data on his own. This is the case with clustering, association analysis, and anomaly detection. Now that we know what data mining is, let's have a look what is inside the data mining model. What do we need that we can predict something? So for all of you that are a little scared of math, this is exactly the scary part. What's inside the model, the algorithms. It's actually not that scary when you have a deeper look inside. So just don't leave the presentation now if you're scared. How are we going to find the right algorithm for our data mining model? There are many different types of data mining functions. Each of them can have multiple possible algorithms to choose from. So which function that is available in the Oracle data mining is the right one for our question, which can be used as a prediction model for skier days. We didn't select this very scientifically, and honestly, you don't have to do this very scientifically, because every data mining function has a name and a short description in the Oracle documentation. If you read it and have a clear question in mind or task you want to solve, it should be very clear which function you have to choose to go further. So let's go through our possibilities. Let's start with anomaly detection. Anomaly detection is listed as an unsupervised data mining function. It is described as a form of classification. It decides if a data point is considered normal or if it is not. So that's not what we need to get our skier days predicted. So anomaly detection is out. But what about association? The documentation says that association identifies relationships within a data set. That also doesn't sound very promising. Let's look at clustering. Clustering defines groups in a data set, but we don't want to have any groups, not for predicting, so not the right one for us. The next one, feature extraction, is for creating an optimized data set that can then be used further in a model. So that would be practical to create a perfect data set, but also not for the predictions. So we might need it for creating the data set. But for the prediction, it is out. What's about the attribute importance? Attribute importance gives us the relative importance of an attribute in predicting an outcome. So which one is more important? So that would be very practical when we are doing measurements and optimizing the model. So maybe later, but not for predictions. That leaves us with the final two, with classification and regression. Both of them can be used for predictions. Classifications are described as models that use historical data to predict a categorical target. And regressions are described as models that use historical data to predict a numerical target. So the only difference is that one predicts the categorical value, like the avalanche risk that can be low, medium, or high, and one predicts a numerical value that is a number. That's why we decided to go with the regression, because we want to have the amount of skiers as a number. As I said, there are different algorithms for each technique to choose from. With the regression that we have chosen, the following two possibilities were available for choosing the algorithm. The first one was a generalized linear model multiple regression algorithm. And the second one was a support vector machine algorithm. And here again, you don't necessarily need to study statistics to decide this algorithm. You could just build two models with the two algorithms and have a look which one gives you the better results. The support vector machine divides the data points into clusters so that they are divided by a clear gap that is as wide as possible, as seen in the left picture. Multiple linear regression is shown in the right picture, and it is used when we want to predict the value of a variable based on the value of two or more other variables. And that sounded very promising to us, and that's why we decided to use the generalized linear model multiple regression model. Now that we know which algorithm that we use, how are we going to divide the data set that we have into two data sets? We need to do more or less this. The thing is, you cannot test with the same data you used for training the model. And that's why you need to split the data set. You still want to use as much data as possible for the training, but also need a certain amount of the data for testing the model. For example, you take 80% for the training and 20% for testing. Now, what's important when we split our data set? A big challenge is if we have skewed data. What does that mean? If we have a symmetric distribution of our data, it looks like in the left picture, the purple one. The median is equal to the mean. That would mean that we have an equal amount of blue dots as we have right dots in our data set. Makes sense, right? A right skewed distribution means that our data is out of balance. This means that we would have many more blue dots than we have red dots. The mean is then further right from the median. The third possibility is a left skewed distribution that the mean is further left from the median. And this would result in a majority of red dots compared to the blue dots. Let's have a look at the possibility number one, how to split the data with. It's Aura hash. And Aura hash generates a hash value for a certain expression. This function is useful if you want to generate a random sample of data. Like we need a random 10% of the data. We can do that with Aura hash. The problem with Aura hash and data mining data is that Aura hash does not know if our data, how our data is structured. It just divides it in half at random. This example you see in the code just halves it without knowing if our data is skewed. So assuming the blue dots and the red dots in our data set, out of the blue and the red dots, they are halved at random without knowing if our data is skewed or not. If there are too few red dots, they could be treated then from the model as outliers or ignored in the training, even though they might be very important for our prediction. While training a machine learning model, this can be a huge problem. But what other possibility do we have to predict, to divide our data into two sets? The second option that we have is the sample clause. The sample clause checks if the data is skewed and regards this in the sample. So it generates an automatic oversampling of underrepresented data points if necessary, or the other way around, it undersamples data points that are overrepresented. This looks as follows. As we have seen before, skewed data is data that is out of balance, as seen in the top picture here. If we now would sample a data set like this with Aura hash, we would probably have only few red dots to train the model with. And then it would be possible that the model treats red dots as outliers. And we don't want to have that. So the sample clause now automatically rebalances this. And there are two ways to do it. Undersampling would mean that we would take fewer of the blue dots and all of the red dots to rebalance the sample. This would result in the sample of the left, where the data points are equally represented. Oversampling would mean we would take many more red dots than we actually have, and we would create copies of red dots to balance the sample. This would result in a sample with an equal amount of blue and red dots to train our model with. That was easy, right? Let's create the prediction model. Now, what are we going to build exactly? Let's have an overview of the process of building the model. We have our training data set that contains most of our data, let's say 80%. We then need a settings table that tells our model on how to behave if we have special settings that deviate from the default. So out of those two, we create our prediction model. To test this prediction model, we have our test data table with the 20% of test data. This table has the same structure as the training data has, but contains different data, and very important, does not contain the target value that has to be predicted. So with the prediction model and the test data set, we are going to make the prediction. It is then possible to compare the prediction to the actual data that we have. That would be the target value that was removed from the test data set. And between the prediction and the actual data, the accuracy results and tells us how accurate our prediction is. That's more or less the data mining process. Now, first, we need to create a settings table because our training data we already have. And this is an Oracle-specific thing that the model just needs this settings table for the creation. It defines the settings in your model that deviate from the default, and it defines which algorithm you want to apply to your model. So the settings table looks like this. There's a setting name and a setting value that you have to define for each model setting that you have. Now, what did we insert? We inserted in our model three main things. The first thing was the algorithm that we wanted to use. This is defined with algo name and tells the data mining model which algorithm it should choose. We have chosen a generalized linear model algorithm that is doing a linear regression over our data points. The second insert enables automatic data preparation. Automatic data preparation is disabled by default, but it is very useful because it transforms the build data according to the requirements of the algorithm. It doesn't change our data table, but it is transforming the data when the model is used. The third thing is the definition of how missing values should be treated. So if we still forgot to eliminate some values that are missing in our data set, we define with the missing value treatment how the model should treat them. Here we decided to use the mean instead of the missing value. It would also be possible to find that missing values are deleted from the data set. Now, to create our data mining model, we use the DBMS data mining package. You have seen this on the other slide before, where the settings were inserted. The create model clause requires us to define a name for our model. It is the object name that will be used further for referencing the model. So when doing predictions, we have to use that name. The data mining functions defines the functions that we choose for the model. In our case, that is a regression, as we decided before. Then we need to name the table that contains the training data. The case ID defines the column that labels the granularity of the data. In our case, that was a date column, but it could also be a numerical column with a sequence or something else. The target column name references the column in our data set that contains the target value that should be predicted. Since the model needs to learn how to predict the skier number, it needs to know which value should be predicted and which values can be used to calculate the prediction with the linear regression. Finally, we reference the settings table that we created, and then the model also knows which settings and which algorithm to choose. That's it. Now we can create our prediction model. If we have the model, how are we going to make predictions? How does that work? Predictions can be done with normal SQL clauses. The prediction function allows us to reference a model when doing a selection against a data set that lacks the final target value, of course, and should be predicted. So we need this predict function. Now let's predict from our data set that we created. When we execute the query, we get something like this, a table with the days and the prediction of how many skiers will ski on a certain day. All the numbers you are going to see here are fake numbers. Unfortunately, I'm not allowed to share the real data with you. But what we can see in the example is that on Mondays, we have a pretty low amount of people predicted, and on the weekend, the number increases. But how do we know if that prediction is accurate? The numbers look great, but are they really as great as they look? The accuracy of a model refers to the percentage of predictions on the test set that are correct, or in our case, how close to the real value the prediction is in average. If we have a 100% accuracy, our prediction would be always right. So the error rate results in 100% minus the accuracy and tells how much not right we are. But how can we measure if we are accurate? The accuracy test should always be done with the test data and not with the training data to allow a fair assessment. So to evaluate the accuracy, we take our test data set, we remove the target value from the data set, and let our model predict the amount of skiers. If we keep drawing a curve like the one in the picture while collecting training data, over time the model should get more and more accurate if we have done everything correctly. So it is also important to regularly test the model again while collecting data over time, because we are not sure if the model really is improving or if it's not. Now let's test our model. What do the numbers say? In the table, you can see our predicted values. When we compare them to the real amount of skiers, we see that they aren't that accurate. The column delta percentage tells us the accuracy in percentage between the predicted and the real amount of skiers. Although some of the numbers are not bad, like we have a 7%, a 13% variation, there are also cases where we have a 100% deviation between the prediction and the real amount of skiers. You can see them in red. So that needs to change for sure. We cannot have a prediction model that is so inaccurate. So we need to improve our model. Since my statistical know-how and the know-how of my research group partners was a bit limited, we needed help here. So we asked around, what can we do to improve our model? And had people that came up with suggestions. We ended up with two main possibilities that we can do. The first one would be feature engineering. That would mean going back to our data set and restructure and redesign the data in a way that would tell the model which features are more important to get better predictions, or also exchanging features that were falsifying the results. The second option was to create multiple models, either one model per weekday or two models, one for a weekday and one for a weekend prediction, to eliminate the variety that we have between the single days of the week. So we decided to go with option number 2, with the multiple models. We did one per weekday and one for the weekends to predict the number of skiers. With one model, we had this setting. We had one training table, one settings table, a model, our test data, and one prediction. Now let's have a look what changed with two models. For the tool model approach, we had to split the training data into two sets as well. So in blue, we have the training data for the weekdays, Monday to Friday. And in green, we have the training data for the weekends, for Saturday and for Sunday. The settings table remains unchanged because we want to have the same settings for both models. So while creating the prediction model, we use the same settings table. So we create also two prediction models, one for the weekdays and one for the weekends. We also split the test data into two sets, a weekday set and a weekend set, and had then two predictions that we combined in a SQL statement to still get our one table that I showed before. Let's have a look at the results that we got with the two models. With the two models, we never had a deviation in a delta percentage that was larger than 30%. As you can see here, there are no more red numbers, what means all the percentages that are under 30% deviation. The difference in the predictions are also improved. When we compare the two prediction sets directly, we see that the number improved from the first to the second approach with the two models significantly. Now, what about all the other statistical numbers of our model? Now, of course, you can calculate everything by yourself, but isn't there another way to do that? And of course there is. With the CAD Model Details GLM, we derived the model information from our skier model. This function is specific for generalized linear models, but there are plenty of other functions for the other algorithms. The CAD Model Details GLM returns the model values like the linear coefficient estimate, the standard error, or the p-value that tells us the significance of the attributes in the model. The second function that we used is the Get Models Detail Global. With the Get Models Detail Global, we derived further information about our model. For example, the F value, R square, or the summarized square error. So all the statistical information that is already in our model and can be retrieved with a simple SQL clause. No need to calculate everything by yourself. You just have to interpret the numbers that you get there. Now, you might ask yourself, what do you need to use those features in Oracle? For the in-database analytics feature, there are no additional licenses required. You can use them already and use the functionalities that I showed you. So our conclusion as newbies in the data mining environment was that it is very easy to learn, but it gets tricky when you have to improve your model and have no deeper understanding of the algorithms and essential statistics. The data preparation really was the big work that we had to do. We spent most of our time arranging and rearranging the data set of the model, creating and optimizing the data set. Building the model was a very small part of it, but we learned a lot while building and rebuilding our data set. That was a lot of fun. So if you want to ask now if I'm going to hand out the slides, yes, I probably will. But as they contain a lot of pictures, they are not very helpful. If you want a written summary of the presentation, you can find it on my Medium page as a blog post. It's a lot shorter than this presentation, but the essential points are in there. Just follow me on Twitter. I'll create a reference after this presentation. Now we have still time for questions. Let's have a look what questions that you had.
Do you see the question, or should I?
Yeah, I see the question.
Okay.
There's one from Bettina. Her question is, how much effort in person months did it roughly take you to create this project? Okay, as I said, we spent most of our time creating the data set. I would say we had roughly for 3-person, like 2 to 3 weeks to build the data set. And then building the model was actually quite easy. We had that in a week. So around 1 month to get the prediction that was preciser than to get a prediction with an accuracy of about 80%, which was enough for our project. Another question from Johnny, didn't you introduce bias by doing the feature selection yourself instead of letting machine learning doing the job? We didn't choose all the features by ourselves. We also used the attribute importance model in the database to get an overview of the features that are considered more important. So we just made a huge set, let attribute importance do the job, and then making tunings ourselves to finish it. Okay, if there are no other questions.
Well,
there is one, yeah. Do you try comparing your results with Python-based approaches and auto machine learning? No, we didn't. We just, since it was a research project, we had to deliver results, and the time wasn't there for doing another approach or compare those with other approaches. So we just used what Oracle database provided and didn't compare it with others. That wasn't done. So is this all possible to do with a good knowledge of statistics and brain work, or was a lot of trial and error necessary to get the first working model, which was close to reality? We didn't have a lot of statistical knowledge, but the documentation is actually quite good, and we didn't need a lot of try and error to get a first model. It was actually pretty straightforward once we knew what elements that we needed, like the settings table, the model. What was really hard was when we realized that our first model wasn't as accurate as it should be. We really had to ask around, what can we do to make this more precise and more accurate? That was the real challenge for us, because that knowledge was missing on our side. Good.
I think there's no more questions. Jasmin, thank you very much for your presentation.
Thank you.
We recorded this presentation and we will publish, so if someone missed this presentation also can see it and hear it again. Thank you very much.
Great, thanks.
Hope you best of luck for your master.
Thank you. Bye.
Bye.